Okay, hello everyone. I hope you're all doing well. So I think you may already have received your exam score or you're about to. Um, but the second exam, the mean had a value of 67 with a standard deviation of 12. I want to remind everyone that this course will be graded on a very generous curve. So because of the difficulties, we're not being very severe in grading. And so you'll find it quite difficult, I think, to fail the course. Uh, all right. Also, I want to point out that the final exam will be very similar in style to exam two. And so if you had any issues with taking the exam through B courses, then please let us know and we'll try to help resolve any problems. Okay, so today we're going to start discussing porous materials. And we'll begin today focused mainly on metal organic frameworks. But before we talk about metal organic frameworks, I want to introduce zeolites, which are a much older and more well-established class of porous solids. So zeolites, in fact, even occur naturally. And these are, in some cases, minerals, now in some cases, man-made compounds. But the word zeolite derives from Greek for boiling stone. And it was observed that some of these aluminosilicate minerals, when you heated them up, steam would evolve. So water vapor would escape. And then when they cooled back down, they could reabsorb water from the atmosphere. So hence the name zeolite. But chemically, zeolites are porous network solids. So they're solid materials, extended network structures that are built up of SiO4 and AlO4 tetrahedra that share corners. And a common example of a sort of cage structure that occurs in a zeolite is shown here. This is what's called the sodalite cage or a beta cage. And in this structure, the black spheres represent a tetrahedral atom, either silicon or aluminum. And the white spheres represent an oxygen atom that links those two atoms. And so these are corner sharing tetrahedral network solids. And these sodalite cages can condense with or connect with various other sodalite cages to form the three-dimensional porous structure of the zeolite. And so in these structural drawings, we're going to represent this sodalite cage with a line drawing. And in these line drawings, each vertex, each corner represents a silicon or aluminum atom. And each line connecting vertices represents a bridging oxygen atom. And so remember that silicon is +4 formal oxidation state. Oxygen is here oxido, so 2-. And if you had just silicon and oxygen in these networks, then you'd have an SiO2 formula and a neutral framework. But for each aluminum that replaces a silicon, aluminum is 3+, and so the charge of the metal oxide network becomes negative as you increase the aluminum content. It becomes more and more negative, and that negative charge can be balanced by cations that lie within the pores of the zeolite. And so the pores in these structures are filled with cations plus water. And depending on how these cages are connected, you can get various different structures which have various different pore sizes. So, for example, if you take this truncated octahedral sodalite cage or cube-octahedral unit, and you fuse square faces with other units and form a simple cubic packing of those units, then you'll form what's called the sodalite structure. This is the structure found in the mineral sodalite. And that structure type is given an abbreviation. So zeolites generally have a 3-letter code that signifies the structure. So for sodalite, that code is SOD. If you connect the cages in a similar fashion, but instead of fusing the square faces, you actually have oxygens bridging between those tetrahedral sites, then you form a more open network structure that is called zeolite A. And that structure type's abbreviated LTA. But you can perhaps see that this different way of connecting the cages leads to larger pores in the middle of this cube of 8 sodalite cages. If instead you connect the cages via the hexagonal faces through a bridging oxygen, then you create this phalgicite type structure. So phalgicite is, again, the name of a mineral. But here you can see there's an even larger pore in the middle of this unit. And then finally, there are different ways of connecting those hexagonal faces. If the sodalite cages form an FCC lattice, then that's phalgicite. If they form a hexagonal closest packed arrangement, then that is this EMT type of structure. Right? And so the shape and size of the pore can be different. Okay, and I want to note that these are just pieces of a 3-dimensional network solid that extends indefinitely through the crystal. All right, so those are zeolites, and zeolites turn out to be extremely useful for many different applications. So one application is in, for example, removing water from organic solvents. So you've probably used these in lab. The zeolites, if you choose the right zeolite, then they have a very strong affinity for water. But if the size of the pores are small, then only water will be able to enter inside the sponge-like solid structure, and the larger organic solvent molecules won't be able to enter. And so this is a sieving effect where you can absorb water, but not larger molecules. All right, and so this has applications then in separating molecules by size. So zeolites are sometimes called molecular sieves because they're like a sieve able to separate things by size. So here you're seeing a plot of bar graph with different zeolites. And the vertical axis is the pore dimension of the zeolite. So the size of the pores within this network structure. And as you vary the structure type, you can see phalgicite has larger pores than these A-type zeolites, for example. But on the right side, you see some molecules, and they're listed here according to their kinetic diameter. So the kinetic diameter of a molecule is a measure of its size, which corresponds to the likelihood that it will collide with another molecule when in the gas phase. And so this is related to the mean free path of a molecule in the gas phase. which is the average distance it can travel before it collides with another molecule. And so you can see variations in these diameters for molecules. And so, for example, in this zeolite potassium A, you would expect that water can absorb into the pores, but cyclopropane, for example, is too large to fit into the pores. And so water could be absorbed at very high capacity within the solid, but these larger molecules above the pore cutoff would not fit. Okay. Any questions so far? Yeah, Amy, please go ahead.
I was wondering if the kinetic diameter was similar to kind of the cross-sectional area for scattering. Is it a
Yes,
similar idea? Okay.
same idea. Yep. Okay. So let's go forward. So besides separations, zeolites have very wide application in as catalysts for chemical conversions. And they're used throughout industry as catalysts for many reactions. One of the big ones that you've taken advantage of would be in cracking hydrocarbon molecules. So here, this is zeolite Y, which is capable of breaking down crude oil into smaller hydrocarbons that you can use for fuels such as gasoline. And so here you're seeing how you make a zeolite. And so usually it's some hydrothermal conditions, so where you're heating water, often not in this case, but often even past its boiling point in a closed vessel that becomes pressurized. And you're taking reactants such as a sodium aluminate source and a sodium silicate source, and perhaps a base, and heating those up for long durations, you form solid crystals of quite complicated chemical formulae. Right? You can see a formula here, and here the aluminosilicate scaffolding is represented by the line drawing. Aquated sodium cations are residing within the pores of the structure, as well as additional water. And so if you heat up this zeolite, all of the water comes out, and you have just this rest of the formula. But that material at 500 degrees C, after some treatment and acidification, can do this hydrocarbon cracking reaction. And so you can see here a huge amount of gasoline is produced by this sort of reaction, and essentially all of the gasoline that goes in your car has been through this kind of process. And as a result, enormous amounts of zeolites are used for this purpose. All right, so you're going to see more on zeolites in lecture on Tuesday, and particularly how transition metals can play a role within zeolites for reactivity. But now I want to move to a more recent class of important porous materials. And they stem from compounds that are known as coordination solids. And so a couple of examples are shown here. But coordination solids are extended networks where you have a metal center, such as this. In this case, you have either copper or zinc as tetrahedral metal ions. And those are linked via cyanide, which can make a linear bridge. And this is just the unit cell but those linkages extend to give then a three-dimensional network. And in this case, the metal ions are alternating, zinc 2+ and copper 1+. And so there are charge balancing cations that are tetramethylammonium cations that are also shown in this structure. But if you stack these unit cells next to each other, you generate a three-dimensional metal cyanide network structure that's related to the diamond structure. And so in these structures, compared to diamond, each carbon atom in diamond has been replaced with a metal cation, either copper or zinc, and each carbon-carbon bond within diamond has been replaced with a cyanide connecting the two metals, right? So these are called diamondoid coordination solids. And in the 90s, in the early 90s, chemists realized in particular that these structure types could be expanded. And so here's an example for, in this case, tetracyanophenylmethane is connecting copper 1 ions, right? And so here you've got a tetrahedral carbon atom with a phenyl group and a CN cyano group that binds the metal. But that also creates a diamondoid type network, but it has much larger pores, right? And so by changing this organic structure, you could change the size of the pores within the diamond network. And so that was recognized as kind of a fun thing to do, and chemists spent some time manipulating and creating different network structures. But it wasn't really recognized that these types of structures could be made to be porous in the same way that zeolites are porous. And so these network structures, they would also have pores that filled either with solvent or ions, or sometimes via mechanical interlocking. But when you heated them up, their structures tended to collapse, and you didn't generate a stable porous network that had open pores. And that was true until really it was shown that such compounds could be porous in the same way that zeolites are porous. And that was shown by Omar Yaghi, who's a professor of chemistry here at Berkeley. And so Omar really was the first person to show that one of those materials could be permanently porous. And Omar has a very interesting history. So originally he's from Jordan, but at quite a young age, even before he finished high school, his family shipped him over to the United States. And so he immigrated to the US. And at the time, he didn't really know much English at all. But he arrived in New York State, in Albany, and he managed to get accepted to a college, so a community college. And he started in college there without, I believe, having even finished high school. And then he transferred to the SUNY University at Albany and completed his studies at quite a young age. And then he went to do his PhD at Illinois, a postdoc at Harvard, and then started a career as an academic chemist at Arizona State University. He moved many times. So he moved from Arizona State. After a number of years, he moved to University of Michigan, and then UCLA. And then finally, about 8 years ago, he moved to join us here at Berkeley. But he's really a very innovative scientist in terms of creating new materials. And particularly, he's been created some very important porous materials. And so here's the original paper that Omar's lab published showing that one of these simple coordination solids could be rendered what's called permanently porous. So when you heat up and evacuate the guest molecules from the pores, the structure remained open, and you could then absorb gas molecules like you do within a zeolite. So this paper was published in JACS in 1998, and I've uploaded it to your B Courses site, and it's a short paper. I encourage you to take a look. But it's essentially just describing the gas absorption properties of this compound, zinc BDC, where BDC is 1,4-benzene dicarboxylate. And that compound is formed in a simple solution reaction between a zinc salt, as we'll see, and the acid form of this dicarboxylate ligand. And it has solvent, both DMF and water, that fill the pores. And so here's how they made this compound. So you can start with zinc nitrate, which is soluble in DMF, as is the acid form of this 1,4-benzene dicarboxylate. The acid form is also soluble in DMF, and there's a little bit of base added here, triethylamine. And that base is slowly vapor diffused into the solution, which is actually a mixture of DMF and toluene in this case. But from that solution, they formed these yellow colorless prism-shaped crystals at the bottom of the vial. And so those crystals have a composition shown here. So zinc 2+, benzene dicarboxylate is a 2- anion. But the point of it is those carboxylate groups can link two zinc ions together. And so here's a figure from the paper showing a portion of the crystal structure. So here there's two zinc ions, and they're each square pyramidal in their coordination geometry. And those two zinc ions are connected each by 4 carboxylate groups. So here's a benzene with the 2 carboxylates, one on either side. So there are 4 of those. And so this is what's called a paddle wheel type of unit. You can see it has a paddle wheel sort of shape. But within the network structure, these zinc 2 paddle wheel nodes are connected through these benzene dicarboxylates. So there would be another one here, up here, over here, and down here. And those connections make a 2-dimensional square network structure in the crystal. And then capping this axial site of each of the square pyramidal zincs is a water molecule. And so this layered structure so here you can see part of the layer. And these are DMF molecules that are in the pores, the square openings of one of those layers. But when they heated up and pulled vacuum on the material, the DMF evolved, and also these waters that were coordinated to the zinc could be removed. And they hypothesized that then led to some fusion between layers to form a rigid, open, porous structure. And to back that up, they did gas adsorption experiments. And so here they were dosing with 2 different gases. So that evacuated solid material, they dosed at 78 Kelvin with N2 gas and at 195 Kelvin with CO2 gas. And they looked at the uptake, how much of those gas molecules were taken up per amount of sample. And so this led them to be able to then observe what's called a type 1 adsorption isotherm. And this type 1, we'll look at the shape in a minute, but the type 1 adsorption behavior here is the same type that's observed for zeolites, and it indicates a truly open structure where gas molecules can freely diffuse in and adsorb on the interior surface of the porous network solid. All right, and then they even went on to calculate a Langmuir surface area of about 270 meters squared per gram, and we'll discuss that as well in a minute. So here are the data from figure 3 in the paper, and you're going to see quite a few of these plots coming up, so let's make sure we understand them. So here they're plotting the pressure, increasing pressure of the gas, either N2 or CO2. And along the vertical axis then is the amount of gas absorbed, and in this case it's units of milligrams per gram of sample. And in these plots, these are collected under equilibrium conditions. So you dose with a precise amount of gas, and you wait for the pressure to stop changing. You measure the pressure, and knowing the amount that you introduced, you can then determine how much gas adsorbed on the sample. And so the filled symbols here correspond to adsorption. As you gradually dose with gas and increase the loading within the material. And so you see a very steep rise and then eventual saturation of the data. And the CO2 is adsorbing to a higher capacity here than N2. And then the open symbols are data collected where you started lowering the pressure. And you can see it tracks along the same curve and then goes back to 0. And so this shape, this Langmuir, what's called a Langmuir shaped adsorption isotherm, signifies a truly open, permanent, what's called permanently porous material. And so, actually, any questions on what we've gone over so far?
Professor?
Yes.
So, does this mean that the gas is not being held within the pores, since once the pressure is reduced, it goes, the amount absorbed decreases again?
Well, what it means is if you maintain a pressure of, say, this pressure 0.5 relative to atmospheric pressure, then that would, under that condition, if you maintain that pressure and held the temperature constant, right? So the temperature is held constant throughout this experiment. Then you would expect this amount of gas to be adsorbed on the surface of the material. And we'll talk about that in a minute. But if you were to lower the pressure and start evacuating the molecules, and you got down to essentially a perfect vacuum, then all those molecules, there wouldn't be any more molecules on the surface of the porous solid. Okay, other questions? All right, if not, let's try to understand some of the theory behind why we see this shape. And this brings us to Langmuir's theory for adsorbed molecules. And this is a really simple model, but it works really well for these types of porous materials. And the idea is that if you have an interface between a gas and a solid, then the gas molecules can have sites that they favor for adsorbing on the solid surface. And the gas molecules will be in equilibrium. At equilibrium, you'll have the same likelihood of a molecule adsorbing as desorbing, right? And the same rate of that. And so you reach some equilibrium for the amount of molecules that are stuck on the surface. And so in this model, Langmuir came up with a simple expression for calculating the surface coverage. So theta here is the fractional surface coverage, the fraction of available sites on the surface that are occupied by a gas molecule. And it's in terms of two parameters, the pressure of that gas, which is readily measured and varied, and essentially an equilibrium constant, what's called sometimes the Langmuir binding constant, this value K. And K in one expression, one way of expressing it, has this form where it's proportional to e to the q over RT, where R is the real gas constant, T is the temperature. In an isotherm, we're holding that temperature constant, hence the name isotherm. And Q is what's called the heat of adsorption. So that's the energy involved with a molecule adsorbing. So when a molecule in the gas phase binds to a surface site, a little bit of energy is released as heat. And so that is Q, right? And so this equilibrium constant essentially reflects how strongly do the gas molecules like to stick to the surface. And if you have a large K equilibrium constant, it signifies that they have a high affinity for the surface, and at very low pressures, you'll essentially saturate those surface sites. If K is small, then you'll have to go to very high pressures to actually reach saturation and full coverage where all those sites are occupied. Right? And so this saturation value up here is corresponding to where all of these sites are occupied on the surface. The surface is fully covered with adsorbed gas molecules. But depending on K, then you could have a much less steep adsorption shape to this isotherm, right? So here, if you have a weaker affinity, it more gradually reaches saturation as you increase the pressure. Right? If you have a very weak affinity, you could have to go to extremely high pressures to fully coat the surface. So just a couple of notes here on how changing the heat of adsorption or changing the temperature should affect the isotherm shape. So first of all, if you increase the heat of adsorption, the strength of binding, then the isotherm will become steeper, and you'll saturate at lower pressures. You'll approach saturation at lower pressures of gas. If the affinity or heat of adsorption is less, then you'll more gradually approach saturation as you increase the pressure. And then the effect of temperature is shown here. If you go to low temperature, then that's going to, you're not going to have a lot of heat available to help drive molecules off the surface, and they'll prefer to be adsorbed. And so you'll see a steeper isotherm shape. Whereas at higher temperatures, you'll have more thermal energy to help drive molecules off of the surface into the gas phase, and this isotherm shape will more gradually rise with pressure. Okay. Any questions on this? Okay, if not, let's keep going. So, so in formulating this theory, or this equation, this simple equation, Langmuir made a number of assumptions. So first assumption was that the system has to be at equilibrium, right? Such that the rate of adsorption of a gas molecule is equal to the rate of desorption, right? And you have to be very careful in collecting this data to make sure that condition is met, because if there are kinetic limitations for gas to diffuse into the structure, then you might not truly be looking at equilibrium data corresponding to just thermodynamics. Secondly, only a monolayer of gas molecules will adsorb at saturation. And so you're going to coat the solid surface with these molecules. They're packing as closely as they can. But a second layer, there's only a very weak affinity for a second layer of gas molecules depositing. So it's assumed that that isn't occurring. And hand in hand with that comes with this assumption that adsorbate interactions are negligible, meaning that the gas molecules don't have a strong affinity for each other. And so that's quite obviously true for molecules such as argon or nitrogen or methane. But it's not necessarily true for molecules like water. So water, which can hydrogen bond with itself, doesn't necessarily need to conform to this behavior. And so an important outcome of this theory is that if you know the amount of gas that will be adsorbed at saturation, as well as the size of the molecule, then you can calculate the surface area of the solid. And this is what's known as the Langmuir surface area. And it's expressed usually in units of meters squared per gram of sample. Right. Okay, so after Omar Yaghi showed that this was possible, that these types of coordination solids could actually, in some cases, retain porosity when you evacuate the guests and behave like zeolites, led to an explosion in research in this area that continues to this day. And it turns out that these metal organic frameworks, or MOFs, there are many very different and useful open structures that you can create. And so chemists have, compared to zeolites, a great ability to tune the structures and the porosity of these materials. And so at the left here, you see a famous, this is an iconic MOF called MOF 5, but it has these tetrahedral zinc 4-oxo units connected again through this benzene dicarboxylate linker. But here the tetrahedral nodes, instead of those zinc 2 paddle wheel nodes, create a cubic network structure. And so the dimensions here are on the order of about 12 angstroms across the pore here, 10 to 12 angstroms. And so these materials, because of the lightweight nature of the scaffolding, these can have enormous surface areas. And so here you're seeing, this is not for MOF 5, but for, this is sort of giving you the properties that are possible within various MOF structures. But BET surface area is a slightly more complicated way of calculating a surface area, but it's generally a similar idea to the Langmuir surface area we just discussed. But you can see these materials can have surface areas now up above 7,000 meters squared per gram. These are the highest surface areas for any known types of materials. And just to give you an idea of what that means, a football field has a surface area of about a little over 4,000 meters squared. So this means that a single gram of this solid material, so just maybe the size of a sugar cube, can have a surface area that's nearly twice that of a football field, right? And that means that per unit mass, these have tremendous number of adsorption sites, positions where gas molecules can stick to the surface, and therefore very high gas loading capacities. So they can be, upon evacuation of the guest solvent, they can be very low density. You can tune the size of these pores even up past 100 angstroms or 10 nanometers. The channels, in this case, the channels actually are three-dimensional network of channels, but they could be 1, 2, or 3-dimensional. The surfaces can be functionalized using chemically. And there are companies now that are producing these materials on ton scale. And BASF was the first to do that. Okay, just to give you an idea of chemical tunability, so that MOF5 structure type, one cube in the cubic porous network structure is shown here. You can vary that chemically just by changing the nature of this linear dicarboxylate organic reactant. And so you can, say, put a halogen substituent on the benzene ring. You can put an alkyl substituent, longer one. You can put another benzene ring. But you can also extend. You can use naphthalene or biphenyl or these longer triphenyl units to expand the pore size within the structure. So this is tunability of, this is a way to tune the sort of functionality of the surface and also the size of the pores within the material. And on the right, you can see how just within this one structure type, this cubic structure type, they were able to vary the pore diameters, the crystal density, and the free volume, the amount of volume that's left when you evacuate all of the guest solvent molecules from these pores. Any questions so far? Okay, if not, that's going to bring us to some ideas for applications or uses of these materials. And so there's a nice paper here from Yagi and coworkers from a few years ago that's also been uploaded to the B-Courses site. And it's quite a general and accessible article, and I encourage you to give it a look. But for the rest of the lecture, we're going to talk about different possible ways of using these materials and also some relatively recent research trying to make these materials specifically for certain applications. And you can see here gas storage, gas separation, catalysis. These are all applications similar to zeolites, but because of the tunability and high surface area associated with MOFs, MOFs might actually be capable of well outperforming the zeolites. And so the simplest application really that you could think of here would be a gas storage type of application. And so the idea is that, you know, often we store gases in pressure cylinders, and you can load up to some pressure, some particular pressure, and you get this steel pressure cylinder delivered to your lab, and it contains a certain amount of gas depending on how high in pressure it was loaded. The idea is that if you were to fill this tank volume as best you could with a porous MOF solid, then at the same pressure as this tank was loaded, you could get a lot more molecules into the volume of the tank. And that's because at that pressure, a lot of the molecules will prefer to adsorb on the surface, right? And so molecules are coming on and off the surface. It's in equilibrium. But within the MOF crystals, you have a much higher density of the gas molecules than in the gas phase. This is essentially saying that the gas molecules have a much higher affinity for sticking to the solid surface than they do to each other. And so with the right MOF, the right surface affinity for a gas and the right pore size, you can really get to some spectacularly high storage capacities within a tank without having to go to high pressures. And so here's just an early example from the Yagi lab. This is showing how another MOF called MOF 177. So instead of benzene dicarboxylate, they used a benzene ring that has a triangle of 3 carboxylates extending from it. And this gives us what's called MOF 177. But here on the right, you can see a plot of CO2 uptake versus pressure of CO2. And again, these are equilibrium adsorption data. But the uptake is given in volumetric capacity. And this line is the capacity within an open volume. If you just have an empty cylinder and you start to fill that volume with gas at that pressure, this is how much gas will go into the tank. If you fill the tank with MOF 177 at any given pressure, here you're seeing the isotherm, and this is how the gas molecules, how much gas you could get in the tank. So a huge boost in capacity. And so, for example, for a CO2 gas cylinder, at a typical delivery pressure, you might get 9 times the amount of gas in a tank that had the MOF within the volume as opposed to an empty tank. And so this, being able to boost the density of a gas at a specific pressure is very valuable for efficient storage of certain gases. And some of the most important examples where we need to boost the density of gases for storage as a fuel are in hydrogen cars, or hydrogen transportation, or hydrogen storage in general. And so, for example, a hydrogen fuel cell vehicle, such as a car, these exist and are being sold and leased. You've certainly seen hydrogen buses that drive around Berkeley. So these cars and buses are powered by a fuel cell that takes hydrogen and oxygen and produces water, but also electricity that can then drive the car. And to be able to drive a decent range, you need to have enough hydrogen on board. Hydrogen, of course, is a very volatile molecule, and it has a high capacity, a high amount of energy per unit mass, but it's very low density in the gas phase. So for a passenger car to be able to drive a similar range to a gasoline-powered car, you'd need to store about 5 kilograms of hydrogen on board. But under standard conditions, 5 kilograms of hydrogen corresponds to 56,000 liters of hydrogen. Right? So this is a ridiculously large volume. Obviously, we can't drive around with a huge balloon of hydrogen attached to our car. And so the hydrogen storage problem is all about how do you pack this amount of hydrogen into this small volume available for the fuel tank in a vehicle. Right? And you'd like to do that without going to extremely high pressures. Extremely high pressures means you have to pay the price, the penalty of the compression energy. You put energy into compressing the gas. And so one very active, still very active field of research for MOFs is trying to boost hydrogen density within such tanks. This is a tough problem. Hydrogen really has weak affinities for most surfaces. A similar application is possible using methane. Hydrogen is really a very interesting fuel because when you use it in a fuel cell, the only product is water, so you don't emit carbon. Natural gas does produce CO2 when we combust it, but not as much CO2 as gasoline. So another idea is to use natural gas vehicles. Same problem as hydrogen. But a MOF can boost, MOF is better at boosting methane capacity in a volume than hydrogen because methane is more polarizable than hydrogen. And therefore it sticks more strongly to surfaces. But this is an example of how MOFs have been tested in the real world. This is a natural gas powered car, and it was outfitted with a large fuel tank filled with a MOF that BASF had produced. And that car was driven essentially around the world along the path shown in white. I think something like, I don't know, 30,000 kilometers. And the point of this test was everywhere it needed to refuel, it refilled with the locally available natural gas. So any impurities in the natural gas went into the tank. And at the end of this long journey, they tested the capacity of the material in the tank and saw that it only lost about 10% of its capacity for storing methane. Right? And so this is a real world test just showing that indeed these materials could be used for a gas storage type application. Okay, so the next level of sophistication for using a MOF for an application would perhaps be gas separations. And so here you want to absorb gases within the MOF, but you want to target a particular gas that you'd like to remove from a mixture of different gas molecules. And so that means the adsorption interaction has to be selective. So for an application like hydrogen storage or methane storage, you might have a very pure gas and you don't have to worry about other molecules competing for adsorption on the surface. But in this application, you have to tune your surface chemistry such that it preferentially binds the target molecule that you want to remove from the mixture. And so the simplest way you would use these materials in an application is you could load up a column with the MOF, bring in the gas mixture in one side. As the gas flows through the column, if you've chosen the right MOF or built the right MOF, then the target molecules, in this case represented by green spheres, will selectively adsorb on the surface. And out the other end of the column will come this purified gas, where you only have, say, the blue molecules. So as you run gas through this column, you'll eventually fill up and saturate the surfaces of the MOF. And at that point, you'll shut the inlet, switch over to a new column, and then desorb the selectively bound molecules in pure form by either raising the temperature or lowering the pressure. Right? And then you can start over. So these materials would be used for adsorption, desorption cycling to separate molecules. And you're adsorbing and desorbing again and again and again to do the separation. Okay. And so separating molecules, it turns out, comes at a huge energy cost. And it's estimated that 10 to the 15% of global energy consumption is associated with chemical separations. And that relates then to 10 to 15% of global CO2 emissions. So a large fraction of our carbon emissions are because we don't separate molecules efficiently. And so here you see a crude plot just showing the relative energy consumption versus the method of separating molecules. And what you see is that distillations are horribly inefficient compared to adsorptive separations that we would do of the type I just described, or membrane-based separations, where you're using a porous material to do separation through a film. And so MOFs can be used for both of these sorts of much more efficient separations if they're designed properly. And so the hope is that we might save tremendous energy by moving from current means of separation to adsorptive and membrane-based separations. And so the largest contributions here by far are large-scale industrial gas separations. And so this just gives you an idea of different sectors of technologies and how they're contributing to CO2 emissions. This is particular for the US a while ago. But here are some examples of separations that contribute to those important separations that contribute to those numbers. MOFs have been developed and explored for trying to do all of these separations much more efficiently. And so I'll just show you a little bit of recent research in this area, and you don't need to understand everything about it. This is just to give you a taste for what research on MOFs is like now. And so an example of a key separation that we need to do more efficiently is the separation of ethylene from ethane and propylene from propane. These separations are done on enormous scales for making olefins for producing polymers. And they're done, unfortunately, they're done by cryogenic distillation. So you see here a picture of a distillation tower. These are people down here, right? These towers are enormous. They're as tall as we can build them. And we do this separation on such a massive scale, but with such little efficiency and such high energy intensity that actually these separations account for 1 out of every 500 CO2 molecules that we put into the atmosphere. And so we need to move away from separating molecules this way. And so if you want to separate these molecules by an adsorption in a MOF, you need to think, what's the chemical difference? And so here, of course, ethylene has a carbon-carbon double bond. Ethane is fully saturated. Propylene, carbon-carbon double bond. Propane, saturated. So we want to try and use the double bond as a way of absorbing ethylene or propylene selectively over ethane or propane. And one can actually use metal sites in a MOF to do that. And so the distinguishing chemical handle here would be you'd want to use a MOF that has open metal coordination sites that could then absorb ethylene favorably over ethane, because saturated hydrocarbons like ethane really don't stick to metal cation sites very strongly. And so here's a MOF structure type that's very important if you want to do this sort of metal coordination based separation. And so it's built out of these organic linkers, which react with a divalent metal salt to form a sort of honeycomb type structure. And you're looking down channels within that honeycomb. The channels here are about 12 angstroms wide. And the metal ions are shown in green. And so here are the linkers. You can see rows of metal ions. And the metal can be varied here. You can use magnesium or these first row transition metal ions. And what's special about this compound, which is called MOF74, is that each metal site within the structure, it's ligated by 5 oxygen atoms from dicarboxylate bridges. But the 6th coordination site is taken up by a solvent molecule, perhaps methanol. Right? And what's special about these materials is you can heat them up, you can evacuate all the methane from the pores, and you can then expose, you can remove that bound methanol and expose a coordinatively unsaturated metal cation site on the surface of the material. And so per unit mass or per unit volume, the structure type has the highest density of coordinatively unsaturated metal sites of this type compared to any known material. And so if you're going to use these open coordination sites to do a separation, this is going to have a very high capacity, meaning you can separate more of those molecules than with other materials per cycle. And so here's a view just looking down one of the channels within this honeycomb type structure. And here you can see the green spheres are these rows of open metal coordination sites, and they're located at the corners of these hexagonal channels. Again, the width here is about 12 angstroms across. And you can imagine that if you're a gas molecule and you diffuse into one of these pores, these channels, then you can't wander very far before you encounter one of these open metal sites. And that might be a site where you stick and absorb to the metal. All right. And so here are some adsorption isotherms for various small hydrocarbons in the iron form of MOF74 at 45 degrees C. And what you see is that methane, which has a very low polarizability, has very few electrons to push around and very wide spacing between their energy levels. And so it doesn't like to adsorb at the iron 2 sites. Ethane adsorbs a little more strongly, but ethylene and acetylene adsorb much more strongly. And that's because those carbon-carbon double and triple bonds can come in and have a relatively strong interaction with the exposed iron 2+ sites on the surface of the material. Right? So these differences in the steepness of the adsorption isotherms are actually sufficient to do an adsorptive separation where you could fractionate and separate all 4 molecules at temperatures above room temperature. And in fact, normally you'd have to do this separation by cryogenic distillation at very low temperatures. And so here is a crystal structure. This is just confirming that when ethylene adsorbs, it's doing so in this metal carbon-carbon double bond interaction, where the charge of the metal is polarizing the pi cloud, pi bond electrons, pulling the molecule close to the site, this metal site. So this is a crystal structure. Because MOFs are crystalline, you can actually do in situ experiments where we've dosed with, in this case, ethylene, and then can collect diffraction data to see where the ethylene adsorbs. And this is from neutron diffraction experiments. So neutrons allow you then, if in this case we're using deuterated ethylene, they allow you to also determine the positions of the hydrogen or deuterium atoms. And you can see under these conditions of dosing, you get 1 ethylene adsorbed per metal, and you're starting to fill up the surface. And so you can actually, in these MOFs, you can then do experiments, and really it's a platform for doing and seeing new coordination chemistry. So here's a similar experiment showing methane and ethane absorbed near an iron site in that same moth. And the way they stick, they can't come as close. They're not nearly as polarizable. They don't have that pi electron cloud to draw the carbon atoms in close. These carbons are much further from the metal. And this corresponds to a much weaker adsorption interaction, and therefore a more shallow rise in the Langmuir-shaped adsorption isotherm. Okay, so these structures are actually fascinating to see and study, and they're not structures you can normally obtain for molecular samples. So you can make MOFs that have open metal sites that are capable of doing pi backbonding. So this is a recent example where a similar honeycomb type MOF was made, but in this case it has vanadium 2+ with coordinatedly unsaturated sites. So vanadium 2 here has then a D3 electron count. Those 3 electrons are in pi type orbitals that can lead to pi backbonding with an adsorbate, including, for example, N2. So this is just showing, this is isotherm data showing a very steep adsorption isotherm for nitrogen compared to methane at room temperature. Normally, nitrogen and methane have very similar energies and affinities for solid surfaces. And they're very hard to separate. So if you have natural gas that's contaminated with N2, then we often don't mine it because we can't do the separation efficiently. And that's because we have to do those separations by cryogenic distillation at extremely low temperatures with an extremely high energy cost. But this material can enable those separation speed done near ambient temperatures. Any questions so far? Okay. All right, so I'm just going to quickly show you a few other facets. We don't have a lot of time left, but a few other unusual things you can do with MOFs. So one of the cool things you can do is you can actually make pores that have geometries that are not seen in any other porous material. And so this is a case where iron 3+ is being linked through benzene diperazolate. After you deprotonate, you make perazolate. So this is pyrazole. And the nitrogen here in the perazolate is a much stronger base than carboxylate. So this forms very strong iron-nitrogen bonds. But the structure that you get has these triangular channels running through it, right? So there's octahedral iron centers running down the C-axis, these planar BDP 2- linkers connecting them. The edge of the triangle here is about 15 angstroms across. But this is a shape you never see in zeolites or activated carbons or porous silicas because they have obtuse bond angles. But within MOFs, you can get these very sharp corners for the pores. So you can imagine if your molecules that diffuse into this structure, at the corners, you could interact with multiple walls, right? Compared to pores that only gradually curve, like in an zeolite. And so that turns out to be useful for separating molecules based on different shapes. So there are some molecules that we'd like to separate where the main difference is just in their shape. And so that's true, for example, for trying to separate alkane isomers, such as hexane isomers. And this is a separation that's done on massive scales, again, for producing gasoline. And what happens here is these hexane isomers are coming out of an isomerization reactor, and they come out in roughly equal molar amounts. All 5 isomers, linear, there's 2 monobranched and 2 dibranched isomers. And the numbers that you see are octane numbers. And it's the dibranched isomers that are very valuable for putting in your gasoline. These are octane numbers that you'd be comfortable putting the gasoline into your car. These other isomers have low octane ratings. They're not as good for the efficiency of your engine. And so what's done is a zeolite is actually used because it can selectively absorb the linear hexane, very low octane number. And that is fed back into the isomerization reactor. And then these other hexanes are all mixed up, but they're put into gasoline. And the average octane rating here is too low for normal use. And so we end up adding a lot of aromatics to the gasoline formulation. Aromatics lead to carbon particulates and soot on combustion. So environmentally, it's very bad. And so the idea here is that you might use the MOF that you just looked at to separate these molecules in a way that zeolites can't. So what this MOF can do is it can actually recognize the differences in shape between these 5 different isomers. And so you can imagine if you're a linear hexane isomer, then when you enter the pores, you can nestle down into this trough at the corner of a triangular channel. And you can have a strong interaction with the surface. But if you're a monobranched hexane isomer, then you can't get down there as snugly, and you don't have as strong an absorptive interaction. You don't have as many van der Waals contacts. If you're a dibranched hexane isomer, then you really can't get down in here. And you're pushed to the middle of this channel, and you have the least strong absorptive interaction. Right? And so it turns out this material is the first that can actually fractionate alkane isomers by degree of branching based on that kind of absorption interaction. Yeah, question.
What like yields that really acute angle of the pores? Is it kind of like a weird oblique bonding to different nitrogens, or what?
No, so the iron centers are octahedrally coordinated, and you're looking down the threefold axis. So the perazolates are connecting irons. So there are 3 perazolates connecting the irons to give these rows of octahedra. And just the way the perazolates bridge leads to that triangular shape of the pore. Right. So if you looked at a side view, you'd see iron centers lined up, and it'd have an iron, nitrogen, nitrogen, iron connection where the 2 different nitrogens of perazolate are linking the irons. And as you go down, there's essentially helices of these perazolates running down here. But they're disposed every 60 degrees to give that triangular channel. So yeah, you'd have to look a little bit more closely at the structure to see exactly how it's connected, I think. Okay, so here are absorption data just showing this difference. So the linear hexane and hexane has a steeper absorption isotherm. These next steep are the 2 dibranched isotherms. And then weakest interaction are the green and blue are monobranched. So 2-methylpentane, 3-methylpentane. The red and orange are dibranched. And those are the most weakly bound, leading to the least steep absorption isotherms. So importantly, this separation can be done while hot, so you can then feed the hot, unwanted alkane isomers back into the isomerization reactor. Okay, so finally, I'll just point out that there is a different way that's now been recognized for doing adsorption in porous materials, which is akin to how some biological systems can bind gases. So we discussed hemoglobin previously. Hemoglobin is this amazing molecule where you get selective adsorption of oxygen at the iron heme sites, but it does it where 4 of these hemes are reacting together. So remember, we talked about when oxygen binds the iron, it causes a change in the structure of the polypeptide backbone that activates the other 3 sites. The result is that these 4 heme sites, they bind and release 4 oxygen molecules all at once, working together. And that kind of cooperative binding or adsorption behavior leads not to a Langmuir-shaped isotherm, but instead to a step adsorption shape isotherm, right? So instead of just rising and then saturating, you have a step and then an adsorption. And this vertical step is associated with that cooperative adsorption. And it allows hemoglobin to either be fully loaded or fully unloaded with very small changes in pressure, right? And so that kind of thing, it wasn't realized that that could be possible in a dense way within a porous solid until relatively recently. You can see this is a very large and heavy molecule for just 4 oxygens binding and releasing. We'd like to do this kind of thing very densely in a porous solid material, and then you could potentially have a very efficient way of doing separations, because a small temperature change or small pressure change could take you from fully loaded to fully unloaded molecules. And so there is a MOF that's been shown to do this with, not with oxygen, but with carbon dioxide. And this is a slice through one of the channels in the honeycomb type structure of the MOF. And it's similar to the MOF we saw before. But each metal here, instead of having an open coordination site, it has a diamine appended to it or bonded to it. And so shown here, you can see this is dimethyl ethylene diamine. And what happens is CO2 adsorbs in this material via a really unique mechanism where it inserts into this metal amine bond. It forms a carbamate that's strongly bound to the metal. And at the same time, you transfer a proton from the backside of this nitrogen to this dangling amine on the next site down the channel. That forms an ammonium cation that wants to interact with the neighboring carbamate. And so you can think of when CO2 inserts at this site, this ammonium wants to interact, it tugs on the metal amine bond and activates it for CO2 insertion at the neighboring site. And so you insert here, 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 and you essentially have a polymer growing down the channel of the pore at each corner of the hexagonal channel. And so here CO2 zips up into these ammonium carbamate polymers, and when you desorb CO2, the polymers unzip. And so this is essentially a cooperative adsorption interaction, much the same way that happens in hemoglobin. But it happens at very high density, and it allows these materials to be used for carbon dioxide separations involving very small temperature and pressure changes to adsorb and desorb the molecules. Right, so these materials, instead of Langmuir adsorption shapes, they show these step-shaped adsorption isotherms. And this is just showing that if you imagine here, we've loaded up the material with our molecules. Oops. A very small drop in pressure, you can go from fully loaded to fully unloaded. With a Langmuir isotherm, you have to go to a very deep vacuum to do that. Or a small temperature increase, and you can desorb at even a much higher pressure. So finally, one interesting thing about MOFs is the MOFs that you saw so far, they're all rigid porous network structures like zeolites. But some MOFs, when you evacuate the guests, they can flex and sometimes collapse to a non-porous form. And so this is a MOF that is collapsed when you desolvate it. But then when you expose it to a pressure of methane gas, it can suddenly, at a certain pressure, methane can force its way in. leading to this adsorption isotherm step. And then upon desorption, you see another step. There's some hysteresis here. And so you can follow this by crystallography, and the structure, it's crystalline when the methane forces its way in and opens the pores. And it's crystalline when it's non-porous and has no guests. All right, so we're out of time, but I think, does anybody have a quick question before we finish class? If not, then everybody have a good weekend, and we'll reconvene on Tuesday.